Hello, ladies and gentlemen, coming to you once again, not quite live from One Take Studios, where we have a doozy of a lesson today. Yes, it's officially been authenticated. This is a doozy. So there's a lot of information here, so buckle your seatbelts and hold on for the ride. We are estimating mu when sigma is known. Alright, so first of all, let's just think about that statement. We're looking for an estimate for mu. This is the mean. This is the mean of a population. In other words, we don't know the mean of a population, so we're looking for something to give us a good estimate for that mean. But the second half of this says when sigma is known. So for some odd reason, we do not know the mean of a population, but we do know its standard deviation, which is based on the mean. So this is not going to be a very common circumstance, but this is a good kicking off point for future things. So we're going to start with this, and in another lesson in the future, we will get rid of the fact that sigma is known, and we will work from there. All right, so for today, what we are trying to do, our objective is to estimate the population mean using sample data. That's logical. If I don't know the mean for a population, I have samples of information, data that I can use, and I can generate an approximation for the mean of the population. Okay, assumptions. We are going to assume that we have a simple random sample, size n, from this population. So we got a population of x's, we don't have all of the x's, but we've taken a sample size, and it is a simple random sample. I capitalize that because that's actually vocab from previous stuff for statistics. Alright, so simple random sample means something very specific. Feel free to look it up. Alright, we are also assuming, based on the title of today's lesson here, is that sigma is known. And one of two things has to be true for this next part. Either the x distribution is normal. So all of these x's that we're talking about in this population, either they have a normal distribution, or what if they don't have a normal distribution, or what if we simply don't know what the distribution is? We have to have a sample size of n greater than or equal to 30. All right, so one of these two things has to be true. Either the x's have to be normal for distribution, or you have to have a big enough sample size to compensate for it. Okay? All right, so here's the thing. Because we are using sample data to figure out an approximation for a population mean, we have to acknowledge the fact that we will probably not be 100% accurate. Okay, fine. So, since we are using x bar to be the point estimate for the mean, okay, point estimate. Again, I capitalize that. This is terminology here. This just simply means that we have one number standing in for the mean. This could be any population parameter, quite frankly, but today we're talking about mean. And it's only logical to choose x bar to be the stand-in for the mean because that's the mean for the sample versus the mean for the population. And we're saying if these two differ at all, which they likely will, because this is a population and this is a sample from the population, if they differ at all, that describes our margin of error, how far we could be off. And this is just absolute value because it really doesn't matter if we're too high or too low, we're just off. Okay, one way or another, we're not likely to hit the nail exactly on the head. Alright, so process that for a moment, thinking. What comes next? Alright, so what we're going to talk about next is what is called a confidence level. Our work in doing our estimate here is only as reliable, focus, there we go, is only as reliable as our confidence level is. So if we don't have good data here, if we don't know what's going on, we can create an estimate, but it may be good, it may be not. It'd be really nice to know how reliable our information is. So this thing called a confidence level, this is kind of important. And this is the statement that we're looking for here. All right, so based on confidence levels, I will explain this, but let's read it, shall we? Right here, confidence levels. For confidence level C, all right, so it's lowercase c, representing confidence level. The critical value z sub c, hold on, so what does that mean? All right, z, that's a z-score. That's a z-score associated with c. So these are the z-scores that work with this confidence level. These are the z-scores that work with this confidence level. They get their own name. It's fancy. It's called a critical value. So if you see the words critical value, they are referring to z sub c. And this is such that the area under the curve, back up curve. All right, so we're talking normal curve, and the area under the curve between one z-score and another is c. Okay, can we make this better? Let's see if we can make this better, shall we? All right, essentially what we are saying is that C is a certain area under the curve. And we've talked about inverse normal before, so if we have the area and we are looking for the z-scores to go with it, we can do some inverse normal stuff here. So inverse normal of this area under the curve will give us the z-scores that set the boundaries for that particular area. Okay, so confidence level of 95%. Let's say that we would like to be 95% confident in the results of our estimate here. What's got to happen for that? All right, so let's think about that from a visual perspective for a moment here. I'm going to sketch. I am sketching a normal curve. And I am saying that I would like the confidence level, or the area under the curve, to be 95%. But notice it's not to one end or the other. We're not left-tailed or right-tailed here. We're talking, I'm looking for this section in the middle, where here's my negative z-score, and here is the opposite positive z-score. And I would like to have 95%, I'm going to write 95% here. 95% of the area is trapped in this section here between these two. Something like that. Okay, so I want 95% of the area under the curve to be between these two z-scores, these two critical values. Okay, thinking again, thinking. If there's 95% here, how much is at each tail end? Well, that means it's 5% left over, so 2.5% must be here. There we go. And 2.5% must be here. There we go. So if we check out our inverse norm stuff, shall we do that? Let's just jump over to the other screen here. Jumping jacks, not jacks. Okay. I'm going to go to menu. And I'm going to go with probability for the moment and distributions, although I could get here through statistics as well. Here's our inverse normal. And if you remember, inverse normal is left-tailed. So if we tell it right now that the area is 95%, it's going to take the 95% on the left. I don't really want the 95% on the left. What was on the left? That 2.5%. So, oops, not that one. There, still not that one. There we go. 0, 2, 5. So I'm telling it that 2.5% of the area was in that space on the left. And I'm okay with doing z-scores right now, so 0 and 1 are perfectly good, and tell it okay. And what do we have? We get a critical value of negative 1 point, we're going to call it 1.96, okay? Negative 1.96. So switching screens again, coming back over here. We are saying that, according to the calculator, running inverse norm, that, I don't like my 6, I'm going to fix it, this lower end z-score here, because we told it to give us the bottom 2.5%, this z-score is negative 1.96. So this is almost 2.5, almost 2 standard deviations below the mean. If these are opposites, if this is negative 1.96, this must be positive 1.96. So our critical values, our z-scores of 1.96 and negative 1.96, are the boundaries for 95% of the area. Okay, thinking for a moment. Need a drink. Way too much talking today. Okay, so let's keep processing this one piece at a time. Again, this is a lot to think about, so pause as you need to. Okay, all right, so we're going to try to piece this together now. Okay. We have this concept of a maximal margin of error. We have already said previously that we know that we're going to be off by a bit. And so what this is doing is this is creating not a single estimate for the mean, for mu. This is creating a window, an interval, in which the mean might be located. And so we are going to talk about this margin of error that we are using to create this window wherein we might be 95% confident. The margin of error can be calculated by doing the critical value, which we just found, so this would be the positive one, the 1.96, times the standard deviation, which we said we know, divided by the square root of our sample size. This can be figured out where this formula came from. This is not that video. All right, if you're taking the AP test, please go find another video. I'm sorry. But I am simply telling you that this is a thing, all right? We can find the maximal amount of area, how far we can be off, by taking the critical value times sigma divided by the square root of n. Okay, so what does this mean? Let's put kind of all of this together here, shall we? Ta-dun, ta-dun, ta-dun. Okay, so the confidence level, which the one that we just did here, for example, was 95%. The confidence level is actually the probability, because we said that not only is this area, but this is also probability. So the confidence level is the probability that the mean for the population is someplace between two values. Someplace in this interval. And we can find out what that is by using x bar as our stand-in, as our point estimate. And from x bar, so everything's going to be centered around x bar, we will go down a margin of error and up a margin of error, down by the e, up by the e, minus plus, to create a window in which we are hoping that mu resides. In fact, we will be able to be confident to a certain extent that mu is going to be in this window. All right, and this is what is called then a confidence interval. Confidence intervals, what we are creating. Again, when we are estimating, all right, so the entire point of this was estimating, right? We are not estimating with a single number. We are estimating with an interval, and that is called a confidence interval. That's based on all this stuff here. All right, so note to self. I left this whole bottom page of this blank so I can scribble on stuff. All right, first note to self. The estimate is not a number. Okay? Boom. The estimate is not a number. Rawr. Don't use a single number. If you're doing that, you've missed the concept entirely. All right? It's going to be an interval. We are looking at an interval overall, not a single number. That's singular. Okay? All right. Not a number. What else do we need to know? Let's think about this. Just a general concept of how this might work. What if I wanted to be more confident than 95%? What if I wanted to be, say, 99% confident? What does this mean? If this were 99% confident, that means that 99% of the area would be here, which would then push out our critical values to make a larger window, a larger interval, with even less on the ends. So if I am more confident, it means I've got more area in the middle pushing my z-scores out, which will then in turn push out the ends of my interval. If I'm willing to be less confident, let's say for the fun of it that I only wanted to be 80% confident. 80% would be the 80% in the middle, leaving bigger areas on the ends. So 80% in the middle would bring my z-scores towards the center, giving me a smaller interval. Recap. If I want to be more confident, I need a bigger interval so that I can be more confident that the mean is in there. If I am less confident, I can create a smaller interval, but again, I'm less confident that the mean will be in that interval. Recap again, because this is something people don't always grasp the first time. All right, if I want to be more confident, that is going to result in a larger interval because it will take up more area. In order for me to be more confident, I need more space in which the mu might possibly reside. But if I am less confident, that's going to result in a smaller interval. Or actually, probably want to say that the other way around. A smaller interval will result in me being less confident. Interval. Because I have a smaller window, a smaller interval in which the mu might reside, therefore making me less confident that it's actually there. Okay. How you doing? Doing okay? Okay. Last page, I promise. We're going to run a full example of this all the way through to kind of see what we've got. So I'm actually just, let's do this. Okay, here's my example. We have Stephen. Currently we know that Stephen runs 3 miles a day. We happen to know that he has a standard deviation for his run time of 1.9 minutes. Why do we know this? I have no idea, because again, we don't know his mean, but we know his standard deviation. However, recently, Stephen has also been keeping track of his runs, and so for the last 2 months, last 60 runs, we know that his average time, his mean for his sample of 60 is 21.4. And again, I can probably put minutes on the end of it. That's 21.4 minutes. So let's do that. I don't know the mean. I would like to find mu. I do have the mean for the sample of 60. And I know the standard deviation is 1.9 minutes. Let's piece all of this together, shall we? I'd like to be 95% confident that my interval contains mu. Confidence interval, 95%, is the probability that we are in here. So let's think about this. Our interval is based on x bar. So I know that the center of this, I've got x bar. I'm going to look at how far I might be off going above x bar, how far my error might cause me to be off below x bar, and that's going to create this interval for mu. Okay, let's take a look at our margin of error here. We know for this example that this is going to be E equals, now alright, Z sub C. We have said that we would like to be 95% confident for this particular problem. Alright, this is always something that's given to you, or something that you can decide yourself if it's not given in a problem. This is the critical value associated with the 95%. This is not the 95% right here. Alright, so let's actually back up by, oh, hey, it just so happens that I've already calculated this. By the way, most textbooks are really nice, and you're not recalculating these things every time, because every time it's 95%, these are going to be your z-scores. So most books will have a listing of popular confidence levels and the associated critical values for those. So we know that my z-score for 95% is 1.96. So I'm going to put 1.96 right there. Times, sigma. Oh, I have that. That's 1.9. So 1.9 divided by the square root of n. N was my sample size, which was 60 runs, so the square root of 60. All right, so this right here, this is going to be my error. So I'm going to, yes. Yeah, all right. I'm going to cheat. I'm going to say that I just typed that in my calculator because I did, but I did it earlier. And that's going to produce something that I'm going to round to 0.48. Okay, 0.48. This is my maximal margin of error. Okie dokie. So what does this interval look like? Again, I'm trying to find out an estimate for mean of the population. I've got 21.4 at the center, standing in as a point estimate for mu. And from the 21.4, I'm going to drop by my margin of error, 0.48, and I'm going to rise by my margin of error, 0.48. So I'm saying I'd like to take my 21.4 and do minus 0.48 for the low end, and my 21.4 plus my margin of error, 0.48, for the high end. So therefore, what I'm looking at is 21.4. So if we subtract, that's going to be 20.92. And if I add, that is going to be 21.88. So my 95% confidence interval says that 21.92 on the low end, less than, hold on, nope, just less than, there we go, mu is less than, on the high end, 21.88. I am saying that I am 95% confident that mu is in this interval. Right here. 95% confident that mu is in this interval. Because this thing essentially has 95% in the middle, so we're setting up the boundaries for this to happen. Okay, so I am 95% confident that the mean runtime for all of Stephen's runs in his entire life, I don't know, he probably started running when he was, I don't know, older than a toddler, is going to be between 20.92 minutes and 21.88 minutes. That is my estimate. That is my answer. That is my confidence interval. It is not a number. It is an interval. If I wanted to be more confident, these numbers would be farther out. If I wanted to be less confident, these numbers would be farther in. How you doing? All right. I showed you this because to me this is really important for understanding things, but I do also want to show you what is in the calculator for this, and then I promise I will shut up, okay? So hang in there just a couple more minutes. Going back to my screen again, I'm going to go to the menu because everything fun and exciting is in the menu, and let's see, we've been running some statistics lately, so let's go there. And, oh, hey guys, look what's on the menu. We have confidence intervals. And because we've been working with z-scores, I think it makes sense that we should be using a z-interval. It's going to say, hey, do you have data or do you have statistics? Data would be a listing like of all of Stephen's run times. We're not working with that right now. We're not even in a spreadsheet. So we are going to go with statistics instead because we have some basic information about his runs. Okay. What do we know? Well, we knew that 1.9 was going to be, there we go, the standard deviation. We said the x-bar for his 60 runs was 21.4 minutes. And again, it was 60 runs was the sample size. And you can set the confidence level to anything. Notice the calculator likes default as 0.95, which is convenient because that's the one that we just ran. Okie dokie. Hey guys, check it out. Do you see what we just did? We said that our confidence interval at the low end was 20.92. Look at 20.919. That's 20.92. And the upper end of our confidence interval, 21.8808. That's what we said. We said 21.88. It's also saying this is centered around 21.4. That's the point estimate. We knew that. The margin of error, I told you, is 0.48. There we go. There's your margin of error. And recap in case you missed it, it's also giving you sample size and standard deviation. So you can run this through the calculator. You can. But again, it is really, really important also that you understand what is happening. Because if you don't have this, you're clueless. You're just pushing buttons. Okay, again, there are not many jobs that you can just push buttons for a living without understanding. So make sure that you understand. All right, deep breaths. It's going to take you a little while to process this. That's okay. All right, that is okay. Yeah, have fun with it.